Okay, we're in section 38. We're doing application integration part 2. Part 1, we did area between curves. Now we're going to be doing volumes. And volumes are probably a little more difficult because visualizing them requires that, one, you know areas, and two, you know how areas relate to volumes. All right, so we'll go through, certainly we'll go through, the visuals that you're given over here, and we'll talk about what they're asking us to do with that visual. We'll read it, and we'll try to visualize it. As we visualize these things, our goal, though, is to set up an integration. The integration we set up, sometimes can be very difficult to integrate, but the bottom line is we need to set up integral, and then we're going to try to integrate the problems as we're given them. These problems are carefully written to work beautifully, right? So we'll do area. We'll also do what's known as an average value of a data set. We'll do one for a finite set of numbers, something you've done in grade school. When you're given a set of numbers, you're asked to add them together and divide by the total number of elements in that set, and you got the average for the set. We'll kind of extend this concept to an infinite sum of numbers, and it's often confused, and particularly when you guys study further, you're going to get what's known as an expected value of a function. That's different than the average value of the function. So what we're going to do is we'll talk about it, hopefully relate back to what you've done in grade school with averages, and then we'll take a look at examples. However, I will say this, a lot of students just memorize the formula with no understanding where it came from. We will talk through that though, all right? Then we're going to talk about the mean value theorem for integrals. It's related to this average value over here, and we'll try to relate it in a way using a picture, right? And then what are we going to do? We'll go to examples. I'll go through the examples. They're basically going to be volume problems where we provide you pictures. The pictures can be helpful. They may not be helpful, by the way. I hope they're helpful. So we'll be providing pictures. We'll be setting up the integrations, and we'll do the integrations. There's also going to be average values. We'll do that. And then you guys will have a chance on your own to try these problems that are similar by doing the homework. And you want to do that. Make sure you can understand these problems over here. They're really not difficult. However, learning is difficult. I know that. Learning is difficult. So what I want to do is go to the whiteboard. Give me a second to do so. All right, you're looking at my whiteboard now. And, certainly as I read this stuff over here, I'm hoping that you're able to follow along. These pictures, by the way, I did not draw these pictures. I took them out of a book. And it's typical, like most calculus books have pictures like this, and it's like an introduction. And certainly if I read it to you, it says, find the volume of the solid whose cross-section. Well, I do see the cross-section. I want to point out what I'm looking at this over here. I'm seeing a cross-section. Those cross-sections, looking at it, look like isosceles triangles. And I'm going to say they actually said that. As soon as I don't even know what isosceles means. Isosceles means that two of the sides are equal. And if it's a right triangle, this is a 45, 45, 90 triangle. All right, so I got that covered. Let me just again find the volume of the solid whose cross sections perpendicular to the x-axis are isosceles. I'm seeing it. Now, what I want to do is I want to relate this back to, I got to get an integral over here, but I got to say this looks pretty strange to me. I'm going to flatten it out a little bit, just the x and y. And what do I notice over here? It looks like it's a line, right? Let me say a line looks about like this over here. Right, I want to point out what I'm looking at this line here. Now, by the way, I'm looking at the line, and what do I notice? It's 4, and that would be 2. So I know the equation of this line, and what's going to be? Y equals, what would that be? The rise would be 2. 2 over 4 is a half. So 1/2 of an x, and the y-intercept is 0. Well, that's easy, 1/2 x. Then what I notice I got this triangle here. And what I'm going to do is I can put my Riemann sum in. That's my little triangle. But what I notice about that little, I'm sorry, I said it's rectangle. That's a rectangle. That's a rectangle. All right, what I want to do is I want to visualize what they have there, though. And what are there? They sort of have that, but it's sort of like, it looks sort of like a box to me now. All right, sort of like a box. So I want to see if I can visualize that. I want to visualize that box. Sorry about that. I'm getting confused with my pen. So I want to visualize the box here. Again, I'm seeing this, and now I got to say, what does this look like? Well, it would look like this now, which is the box. Someone said, weird looking box, triangular box, but I need the volume of that box. I need the volume of this box. And I want to tell you what the volume of the box is going to be. It's going to be the surface area, which is really easy. It's 1/2 base times height times the thickness, which I'll call W. Let's see if we do this one step at a time. Volume is 1/2. Well, I don't know the base, but I do know the height of it. And why is that? The height of it, I got to plug in my battery now. Give me 1 second, running low on juice. Okay. I do know the height of it. What's the height of it? The height of it is this. But if it's isosceles, the base will be the same. So let's write this down. The base at any point along the x's would be 1/2 of an x. The height at any place along the x's, isosceles, is still going to be 1/2 of an x. What's the width of it? Well, it's a differential, which is dx. So that's the volume of one little tiny box. Let's put that down. V, what's that going to be? X squared over 8 dx. What am I going to do now? Add those little boxes together from 0 to 4. I'm going to add all those little boxes together. And what do you get there? Well, I got my integral. Let's put down the integration. You're going to get x cubed over 24, linear integration 0 to 4. And again, I want to repeat this. I'm not beyond make a mistake. I want to point out, if I do make a mistake, I need to go back over my work and look for it. And we're encouraging you to do the same thing. Make a mistake, go back over your work and look for it. This is 64 over 24 minus 0. Well, I got to reduce that. I'm going to say 8. 8 goes into 64 8 times, and it goes into 24 3 times. So I'm going to say 8/3 cubic units. I don't know. Maybe I made a mistake. Let's go back over here. And what do I see? I see 8/3. What did they do? They gave us a visual. They did they wrote down the integral, and then they did the integration, right? Let's talk about the average value. And I'm going to point out, for a finite set, it's really easy to do that. For a finite set, what you get, you'd have samples, x1, x2, x3. Whoops, I'm sorry, I didn't mean to do that. I'm just writing down the set, not adding them together. x3, yada, 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 up to xn. So this is going to be our sample set. What do we do to get the average? The average, very simple. All you have to do is add those numbers together. So x1 plus x2 plus x3 plus yada, 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 up to xn over n. That would be the average. What do we typically call that? Well, x bar. All right. So they give it an example over here. I wouldn't worry about that example over there. We really need to get to the average value of a function. All right. So I'm going to skip that example. And what I'm going to do is I'm going to talk about average value of function. It's a problem though. And I'll tell you what the problem is. The problem is understanding the formula. Right. So what I'm going to do is I'm going to say, we want the average value of the function on the interval from A to B. Now I had to say that this is the average value. So I'm going to write f a v g, the average value of f on the interval from A to B. So what you'd have to do is you have to start taking sample points. So let me say f looks like this over here. So you take sample points. You might take a point here, a point there, a point here, a point here. That would be one. Maybe I went too far with that. Let me get my eraser out. So if I were to take those sample points, I'd have to evaluate f here. Well, that's f of a, right? Over here, I need another sample point. We'll call it C. F of C. I would take another sample point over here, D, call it f of D. This is the value of f. And this would be f of B over here. What would I do? I'd add it together. F of A plus f of C. You get the idea. Plus f of D plus f of B over, oh, there's 4. I could do that. Here's the problem now. That's a sample. I want to take every single point on the interval. So let me erase this. And I think I've seen this before, but it looks sort of familiar to me. I'm going to erase all this nonsense over here. Erase all this over here. And what I want to do is I want to start talking about, if I start taking every point, so I'm going to say xi, whoops, xi is going to be some number on the interval a to b. I'm going to tell you what the set looks like. So it's going to be x1, x2, I did it again. I got sums on my mind today. x3. By the way, I'm not looking for the average value of x. There's n sample points over there. N of them. I'm not looking for the average value of x. I'm looking for the average value of the function. So it's going to be f of x1, f of x2, f of x3, f of x4, yada, 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 up to f of xn. Let's write that down. Still a sample average, by the way. So f average, this is still a sample average. We're sampling. What do you get over here? F of x1 plus f of x2 plus yada, 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 up to f of xn over n. That's f average. Now, by the way, I'm going to relate this back to something we've done in the past. And what we've done in the past is we've done these Riemann sums. And the way to do that is you're going to be taking a bunch of points along the interval and you're going to have a partition down. Now, what was the partition size, if you remember? Well, its partition is going to be b minus a. I think you remember me doing this before. Over n. And then what would I do, if you recall? I would have to take sample points along the interval, and they'd be equally spaced, but let's not worry about that. Let's just simply write down what those points would have been in kind of an abstract way. So I'm going to say I would have taken 1 point here. I would have taken another one. I would have taken another one up to this over here. All right. I think you remember me doing this. We called it a Riemann sum. And then I said, this could be rewritten a little differently. All right. This could be written differently. All right. Now someone says, what do you mean it could be written differently? This over here could be written as an integration. The only way I could do that though, and again, this is an approximate area now. We've done this before. By the way, I want to do this though. We'll get there later. So I do approximate area. What am I going to do? I'm going to look at the limit as n goes to infinity of this guy over here. And what would that be? Let's write this down. B minus a over n. That have something like this, right? Sum I equals 1. Let me use a different n over here. Put this n over here now, big N. I think we did that in the past. N, and this would be f of xi. What's this over here? Well, we did this in the past, just an integration problem. And what's an integration problem going to be? Let's write this over here. It would be from a to b f of x dx. But you know what? This is really what I want. And what I really want is f average for the function itself is when n goes to infinity. So I'm looking for this, and I think I see it. So this thing as n goes to infinity is this thing over here. I need to get rid of the b minus a. So write this down. Limit as big N goes to infinity, 1 over n, sum I equals 1 to big N, f of xi is 1 over b minus a, integration a to b, f of x dx. This is f average. All right, right over there, f average. You know what? I forgot to put the big N here too. Sorry about that. Let me see if I did that. No, I'm good. I'm good. So I think we got it. Let me go back over here in the notes, point out where it is in the notes, right over here. And we got it. All right. Let me outline that for you as I'm reading it. We just covered it. The average value of a function on an interval from a to b is given by this. This formula will be discussed in class. We did do that. Let's look at an example. And the example given to us is, given the graph f of x, find its average value. Well, they gave me the graph, but I don't think I really need that. I'm going to write down this formula. What's the formula going to be? Well, it's going to be this. Let's see if we can do it. F average, whoops, I did it again. Did it again. Let me push this over a little bit. I'll come back to it in a second. F average, AVG, is equal to 1 over b minus a. Well, what's that going to be? 2 minus 0. I'm just looking at the numbers. Integration 0 to 2, f of x, which is x squared, root 10 minus x cubed, dx. I'm just using the formula. I want to see if I can do the integration now. And it might be tough. These problems are carefully written though. 1/2. Let's see what we get over here. I got to use u substitution. I'll put this down for you. U is 10 minus x cubed. Du is minus 3x squared dx minus 1/3 of a du is equal to dx. I'm going to be very careful here. If x is 0, what would u be? 10. If x is 2, what would u be? 2. Right? What's this guy right over here? It's going to be u to the 1/2 power. What's this guy? X squared dx. Whoops, I forgot to do that. It's minus 1/3 of a du. Let me write that down. I got to clean this guy up and do the integration. Minus 1/6. I'm just associating these two numbers together. What's the answer of u to the 1/2? Add 1 to the exponent. What would that make it? 3/2. You're going to divide by 3/2 or multiply by 2/3. And you're going to evaluate it from 10 to 2. I know this is tough. What do you get over here? Minus 1/9 2 to the 3/2 minus 10 to the 3/2. By the way, for some students, they're done. Put a box on it. You are done. All right. I'm not done yet, though. I'm going to write a little bit differently. The way I'm going to write this down is I'm going to say a common denominator of 9, and it's going to be 10 root 10 minus 2 root 2. I prefer that answer over here. By the way, this is fine. This is fine. Let's look at the key, though. I'm not saying we're done, by the way. I'm just looking at the key. And the key, I'm looking at the answer over here, and that's the answer given to us. So I feel pretty good about that. So I want to keep reading. It says, given the graph of that, find the average value. I'll look at the graph on the next page, by the way. But we did the work. All right, we got that. And now someone's going to say, what else do you want to do? Well, I'd like to find out where the average value is. Like, where in the crowd of all the numbers is there a C that takes on that value? So my claim over here is, and again, it might seem difficult to you, there's going to be a C right? There's going to be a C in this region. And someone says, what region are you talking about? It's going to be a C on the interval between, I got to make sure I'm doing this right, 0 to 2, such that F of C is going to equal to the F average. This makes sense because if you look at the function, whatever it looks like, and you add all those things together, the average has got to be somewhere along the interval. That's what we're looking for. What are we looking for? Where are we going to find the actual F average? Where's the average guy along that interval? I'm going to say there's going to be at least one of them. There's only one average guy everywhere. All right. So let's take a look at it. And let's see if we can do that. So what's F average? And I'll write this down for you. It's root 10. I'm sorry, 10 root 10. What am I saying? Minus 2 root 2 over 9. And what's F of C? Well, you know what? F of C is actually C squared, square root 10 minus C squared, C cubed, I mean. By the way, this is not easy to solve, but it can be solved. It can be solved. Solve for what? C. Let me repeat this. C will come between 0 and 2. You may find another C, but we only want to see between 0 and 2 in the crowd, so to speak. All right. So I'm going to say you could do that. I used a computer to do that, and I got this number over here. I do want to look at the graph, though. Right? Where's the graph over here? So I want to point out what we're looking at is we're looking at the graph of F. We computed the average. This was F average. We computed that number. All right. Yes. When I say computer, I use the computer to get approximate. And what are we doing over here? We're looking for the C. And the C is going to be some number. I can say around 1. You know, C of 1 is equal to the average value. All right. So the deal about this over here, you start to realize that really what are we doing? We're taking something like this. I'll go to the next picture in a second. Sorry about that. Which has an area. And what are we doing? That's a really strange looking area, by the way. And what we're doing is squaring it. That's all we're doing. We're squaring it. So my claim over here is the area under the curve f of x is identical to that square part. And what's the area of the square part? F average times the length of the interval. Let's look at a better picture. It's over here. I want to claim over here is what I'm doing is drawing F average, finding the C. That can be tough sometimes, and realizing this would be F of C. The area of this thing over here would be 2 units times F of C, and that would be identical to the area under F for that. That's visualized. What are we visualizing? The mean value theorem for integrals. Let's go over that though, and let's make sure I understand what they're saying over here. What are they doing? Taking that average value formula, reworking it, and they get a pretty simple statement. What statement are they getting? They're getting the statement of the mean value theorem for integrals. Sorry about that. Okay. If f is continuous on AB, then there exists a number C between A and B. What's that going to be? That's the average value of it on the interval from A to B for f of x. Let me get something over here. Real simple stuff. All right. Real simple stuff. All right. So when I say simple stuff, it's simple if you visualize it. All right. We will go through examples, by the way. The examples we'll go through will be on the starting up with after we're finished with this now. So when we come back, we'll do the examples. What examples are we doing? We'll be doing the average value of the function. Make sure you study this. I'll write this down for you. You want to study this? I'm hoping you're able to follow my presentation for that, how to get the average. We did an example of average value. Although I didn't find the C, a computer can find the C sometimes if you want to look for it. What else do? We did volumes, right? Introduction, though. I realize it's tough. Here's the deal, though. We just did a few examples. We have to do more examples to pound this information across. What are we pounding across? Volumes, average value, and mean value theorem for integrals. All right. And we'll come back and we'll finish that up. Thank you.